Welcome to RF and millimeter wave IC design class. This is your lecture number 6, and today we'll continue our discussion on the effects of nonlinearity. We'll spend some time to see how we can simulate a 1 dB compression point of an RF circuit in Cadence, and also we look at some of the numericals, one numerical specifically on desensitization. So from yesterday's class, I hope this is clear for you guys that desensitization is actually when you consider an interferer, a strong interferer received at the receiver along with a desired signal, and because of the intensity, because of the amplitude of the interferer, even the desired signal, even your system or your circuit can be insensitive to your desired signal, and that is otherwise called as in such a case your interferer is otherwise called as a blocking signal or a blocker. And to in the same line, let us consider a numerical and try to understand a little more about this desensitization. All right, so this is your question. You guys can try this. Uh, a low noise amplifier can be modeled as y of t equals alpha 1 x of t, alpha, this modeled as y of t equals alpha 1 x of t plus alpha 2 x square t plus alpha 3 x cube t. Given that alpha 1, the fundamental gain component is 10, alpha 2 is given as minus 2, and alpha 3 is given as minus 0.5. These are the coefficients given. Now the input to LNA are desired signal at omega 1, which is having a peak amplitude with a peak amplitude of 1 millivolt, and blocking signal. I'm just calling it as blocking signal or interferer blocking signal. It is appearing at a frequency of omega 2 with a peak amplitude of 2 volt. Now the question is, there are two parts to this question. A part says that assume there is no filtering at the front end. Assume there is no filtering before LNA. If there is no filtering before LNA, what is the gain of the desired signal? What is the gain of desired signal? This is first part of the question. And the second part of the questions, okay, let us solve this first part and then we can move on. So let us try to understand this question and solve the first part, and then we can move on and discuss about the second part. So given that a low noise amplifier which is modeled using a third order nonlinear polynomial, and given the coefficients alpha 1, alpha 2 and alpha 3, there are two input signals. There are two signals at the input. One is desired signal at omega 1 and another one is an interferer at omega 2 with the corresponding amplitudes as 1 millivolt and 2 volts respectively. Now, if the front end is having only LNA, there is no filtering before LNA, what will be the desired signals gain? That is the first part of the question. So can I get answer from someone? can just check with Parth Rajanish. Are you there?
Yes, sir.
Yes. Parth, can you tell me what will be the gain of the desired signal, or the expression of gain?
Yes, sir. Yes, sir.
Yeah. You may refer to what we have discussed yesterday. If you're not able to find, I can check with someone else.
Sir, I'm confused between the three, sir. Like when A is small, when A can be big.
All right, you can consider with both amplitudes. No need to neglect anything.
Okay.
So considering both A1 and A2, because hope you understood that there is A1 and A2 here. There are two
Yes, sir. Yes, sir.
amplitudes. Yeah. Okay. So for better clarity, what I'll do here is let me consider the front end of a receiver antenna, and this is LNA. LNA being non-linear. Now at the input there are two signals. One at omega 1 and another one at omega 2. This is 1 millivolt and this is 2 volt. This is A2 and this is A1. Now tell me, what is the gain of desired signal?
Sir, I'm not sure.
All right, no problem, no problem. Yeah. Uh, who else is there to ask? Rahul Chikodi.
Yes, sir.
Yeah.
1 second, sir. I'll just tell you.
Yes.
Sir, is it alpha 1 plus 3 by 4 alpha 3 A1 square plus 3 by 4 alpha 3 A2 square?
Yeah. The third term is not 3 by 4. It is 3 by 2. That is what I
Sorry, yeah,
corrected today
that's 3
morning.
by 2.
Yeah.
Yeah, yeah.
Yeah. Yeah. Thank you, Rahul.
Yes,
Yeah.
yeah.
So it is alpha 1 plus 3 by 4 alpha 3 A1 square plus 3 by 2 alpha 3 A2 square. Yes, this is the gain of the desired signal. And please calculate and let me know what is the numerical value. Those who are getting answers can put in the chat box. I can look at that. Any answers? Those who are getting answers can post in the chat box. Alpha 1 is given, A1, A2, and alpha 3 values. All values are there. Yeah, it is 6.99. It is 7. Yeah, it is roughly 7. Very good. It is 6.99 or it is 7 volts per volts. Yes. That is a gain of the desired signal. And that is straightforward. And with the initial observations, what we made on a third order polynomial, nonlinear, characterized by a third order nonlinearity, we know that. Now, the second part of the question goes like this. If so, previously it was mentioned that if there is no filter, what is the gain? Now the question is, if we insert a filter, before LNA, if we insert a filter before LNA, and minimum gain for the desired signal minimum gain for the desired signal is 19.5 dB. Hmm. So given that there is filtering and the minimum gain for the desired signal is 19.5 dB, the question is by how many dBs, must the filter attenuate the blocking signal? By how many dBs must the filter attenuate the blocking signal? This is the question. So try to understand this. Now we are inserting a filter before LNA. That means the initial amplitude A1 and A2 will definitely get altered when it reaches the input of LNA. And also given that the minimum gain of LNA now is 19.5 dB, in that case, by how many dBs must the filter attenuate the blocking signal? That is a question. So you guys can try. Yeah, I saw all the answers you guys posted for the previous part of the question. That is right. Now can you try this part? It is always better to visualize like how this, what will be the, how the signals are processed in this specific receiver. For that, it is always good if you can represent using blocks. So this is the LNA which we previously considered. Right now, before LNA, we have a filter. A filter is inserted before LNA. So this is your filter, and the input is reaching the filter through this antenna. Right. So this is how now the receiver front end will look like. Now signals appearing at the antenna are of as we mentioned before, A1 and A2 amplitude at omega 1 and omega 2 with amplitude A1 and A2. Right. Now the idea of this filter, or the filter is constructed in such a way that yes, Anish, I think you are uh, Anish, you're asking answer for this part as 2.6.
Yes, sir.
No, Anish, can you check it? Check that again.
Okay.
Yeah. So at the input side, you have A1 and A2. Now you have filter. So the idea of filter is just to attenuate this A2 or the blocking signal. That is the idea of this filter. So at the input of LNA, you will not get A2 directly. You will get a slightly different amplitude. So I'll wait for 1 or 2 minutes for you guys to try for this question. And if you are not getting, I can definitely help you. Any answers? Roughly 0.5 dB. A2 at LNA is 0.864. Mm. So Vinod, you meant to say that at the input of LNA, you will get an A2 value of 0.864. All right, yeah, that is right. Rahul, 0.5 dB I didn't get. Let us see whether you also is referring to the same A2 amplitude. Okay, for others who are still trying, yes, Kashish, 0.86 A2 is right. Yeah. Yeah, for others who are trying even now, I can help you. So A1 and A2 are the amplitudes at the input of this and this the receiver front end. And now, so A2 is the amplitude of the interferer here. But after filtering, definitely the amplitude of A2 will get reduced. That is the role of this filter. So I'm just marking this amplitude as A2 dash, right? And A1 as such, there will not be any effect of filter on A1 because the filter is not meant to filter out A1, omega 1, but rather omega 2, right? Now it is given that minimum gain for the desired signal, should be equal to, let me call it as G minimum of LNA. It is given that it should be equal to 19.5 dB. So can you guys convert this into volts per volts and let me know the value? What is 19.5 dB? Somewhere close to 10. Yeah, 0.866 Pratap, that is right for A2. Yeah. So what is 19.5 dB? It is 9.44. Yes, that is true. So that is the minimum gain. Now, when I write the gain expression here, I can write it as alpha 1 plus 3 by 4 alpha 3 A1 square, the same previous expression I am taking. But when I write for A2, it is not A2, it is A2 dash square, because A2 is modified as A2 dash through this filtering operation, and this can be equated to, this is A2 dash then square. Now this can be equated to 9.44. So in this alpha 1, alpha 3, A1, everything is known, and you can definitely find A2 dash from this. And if you calculate this, you will get A2 dash as 0.86. 0.86 volt is A2 dash. Yes. Now, if 0.86 is A2 dash, the question is by how many dBs must the filter attenuate the blocking signal in order to have a minimum gain of 19.5 dB for the LNA. So, how many dBs must filter attenuate the blocking signal? Blocking signal is A2 here and it is A2 dash. Now, the gain or the attenuation of the filter can be easily obtained. So, I'll write it as G of the filter. It is basically attenuation. Or I'll write it as gain only. A2 dash is output, A2 is input. If I take this ratio, it is equal to 0.86 divided by 2, which is close to 0.43. Or if I convert into decibels, this will be equal to minus 7.2 decibels. So minus 7.2 shows that this is attenuated, or this is attenuation. All right. Yeah, minus 7.3 dB. True. Correct. All right. I hope this is clear. This part is clear. Yes, Lalit, go ahead. Yeah, please, please.
So basically, this numerical is based on the concept of gain compression, or like I'm not
Uh,
able to correlate to what you're.
oh, sorry. This is actually to understand the effect of another signal interferer coming along with your desired signal. So you can see that in this specific case, in the first point, when you have directly LNA, we obtain the gain of the signal as some 7 volts per volts. But later we saw that, so in the question itself it is given that there is an interferer coming along with that. Now we are trying to reduce the effect of that interferer by connecting a filter at the input side, and thereby we so we try to find basically this problem dealt with the filter. So how we can properly attenuate, not properly attenuate, how we can attenuate your interferer or blocking signal by maintaining a specific gain for your LNA. I would say this is more related to what we just discussed as desensitization or blocking, because the signal coming along here as omega 2 is an interferer.
Yes, sir. So shouldn't the filter try to completely filter out the higher component, which is not the message
Yes,
signal?
yes, yeah. That is a good question, Lalit. So what we are expecting is whenever we use a filter, um, the signal at omega 2 should be completely eliminated. That is what we expect, right? Now, but
Yes, sir.
that expectation, and when it comes to reality, we do not have a filter, or there are there are a lot many design things we need to understand when we place a filter at the front end. The very first thing is, I have no option actually to have a filter having this kind of response. We call this as brick wall response, right? I cannot get a
Yes, sir.
filter which can definitely have this kind of response. So I do have filter with a pass band, stop band, and there is a pass band and stop band, but not with this kind of response. So whenever we employ a filter, again at the front end, we will not be able to selectively pick this single frequency, because again all these things we'll even discuss when we start our architecture study. When I try to keep a filter with this kind of response, you can see that the selectivity of the filter is very high, right? So I'm trying to pick only one single frequency, so this will definitely demand me a very high q factor. So realizing a high q factor is also like practically realizing that is difficulty.
So, but
So
this also depends on omega 1 and omega 2, right? Like, because when you discussed an example before, you said that if they're closely placed, then it's hard to filter it out. But
yes,
in this
yes, yeah,
question,
yeah.
they didn't mention omega 1 and omega 2. So, we can also consider a case where you can get a gain of 19.5 dB, excluding A2 as well, right?
Yeah, so in that case, so if your point is if your omega 2 is very far, then this will not come into picture at all, right? Your A2 will be
Okay.
completely eliminated, right? Even that
Yes, sir.
that information is not given in the question. So I assumed, or I'm like that assumption is taken for granted, as it is omega 1 and omega 2 are closely placed,
Okay.
or it is not that easy to eliminate omega 2 from omega 1.
Okay, sir. I understood.
All right, yeah,
So,
yeah.
so signal one should
Thank
also get minus 7.29 dB
Uh,
attenuation, is it?
not exactly, because no, even though they are closely placed, it is not. We designed this filter to remove this omega 2 component, not the omega 1 component.
Okay, sir.
All right, yeah. Yeah, that is why even the question says that the minimum gain for the desired signal is 19.5 dB. So even though we are placing a filter, making sure that at the end of your at the output of your LNA, you have a minimum gain of 19.5 dB. I hope it is clear. So now we will quickly move to the simulation of the previous class 1 dB compression point. So if you have questions, then definitely I can take questions after showing the simulation part. All right. I hope you can see the screen, Cadence screen now. Can I get some response? Can you see the Cadence screen? Okay, yeah, thank you, Rahul. So this is the same previous LNA circuit what I have kept, and today we will look at how to simulate this 1 dB compression point. Yeah, so before that, this is just to familiarize you guys. These kind of simulations are available in Cadence, and as I mentioned, we will be doing LNA as one design as a part of our course project, like for the 20 marks or whatever it is. So those details I'll share you very soon. All right. So now you can see the analog design environment here. I have enabled 3 analysis here. The SP analysis is for the last week where I was showing you the harmonics. Now we can see one analysis here called PSS. PSS is called as periodic steady state analysis. I'm not going to the details of the periodic steady state analysis, why we are doing such an analysis, what is this shooting and what is this harmonic balance. There are lot more technical details behind this. For the time being, I want you guys to see how we just simulate this and see the output waveform. But when you start designing this LNA, you can look at the design, the technical details of this analysis in a little more detail. So what you are seeing here as FRF1 is the single input frequency what I have given 2.4 giga at port 0, and I have just 10 harmonics. That is same as the previous this one. So one addition, so you can do even the harmonic balance, this SP analysis or PSS analysis or all these analysis. You will get even harmonics after doing a performing a PSS analysis also. Okay. So now, so what we are trying to do here is we want to plot input amplitude versus output amplitude of this particular circuit, right? So the input amplitude is PRF. I have given the input amplitude variable as PRF. I'm varying PRF from a low value to a high value, and I'm going to see how your output is responding, right? So from yesterday's class, uh, hope we can see this. So from yesterday's class, we saw that, we saw that when you vary input amplitude versus output, this will be your violet line will be your ideal straight line, which is linear. We are not considering any non-linearity then, but in practical case, your gain will compress and it will fall. And we are measuring that 1 dB fall from your ideal line as 1 dB compression point. And this is what we are going to simulate now. All right. So, yeah. So for that, what I have done here is I have enabled this analysis called PSS, and the single input frequency FR1 is selected. But one additional thing what I have taken here is I'm actually doing a sweep here because I want to sweep. I want to vary input amplitude. So I have taken the variable PRF. PRF is your input signal amplitude in dBm, and I'm varying that from minus 50 dBm to 30 dBm with a step size of 5. That is only the single setup what I have done. So after that, I'm just so PSS analysis with sweep of input amplitude I'm doing, and I'm just simulating it. Yeah, I think the simulation is done. It is successful. Yeah. So I'm trying to plot the results from direct plot main form, and in this main form I'll be clicking on sorry, the system is slow. Okay, so what you're seeing here as direct plot form is the of PSS analysis, and if you click on the PSS analysis, all these things can be plotted. And what I have done here is I have selected the compression point. I'm selecting in the port, which is the output port here. The format is in the form of output power. But this is what I'm measuring is 1 dB compression point, and I'm taking the fundamental frequency to 0.4 giga here. Now, if I select this output port here, I'll get the simulation result of this 1 dB compression point. But it's taking some time. So I have, yeah, I think it is done now. Yeah, so I have selected PSS. Yeah, I'm just replacing the plot because already I have plotted it. Yeah, selected compression point. Output power 2.4 giga. It is in, I'm just selecting the output port here. Yeah, so that will give you the compression point. I hope you can see this. I'll try to okay, I hope you can see this. What you're seeing in the green line is the linear, the ideal graph, the without considering any non-linearity. And what you're seeing in this yellow or this orangish line is your compression curve. You can see that as your input amplitude increases, your output is getting compressed here, and the 1 dB compression point is automatically displayed here by the simulator. You can see that input referred 1 dB compression point is equal to minus 14.8758. Now, why it is called as input referred compression point is because we are actually referring this back to the input axis. Now, at the same time, if you mark this towards the output axis, we call it as output referred, but generally input referred 1 dB compression point is what we usually use to understand about non-linearity, because we know that how much more input we can give to a particular system. All right. So this is how we usually simulate 1 dB compression point for any RF circuit. I'll definitely keep the screenshot in the notes. So this is one sample simulation what I want to show you, because since we are learning about compression point, it will be good if you see a simple simulation, but it will give you more idea when you design a circuit and then you work on this and when you measure the 1 dB compression point. All right. So with this, I am winding up today's session, and if you have questions, you can ask. Thank you for joining.